Alright, so this is Math 331, problem solving, lecture 28 plus or minus 1. So we are talking about Putnam and triaging. So when you look at the Putnam problems, this is very similar to the medical where you have a bunch of things that are killing you, and you look and see which one do I have a chance of dealing with, and which ones are just hopeless and should not even look at. So a lot of the problems, you should not spend any time really looking at them on the Putnam. Quickly glance at the question in case you happen to have a great insight. But for the most part, spend your time on the problems where you think you have a chance of writing something non-trivial. If you think any of your professors here are stingy in terms of partial credit, the Putnam graders will take this to 3 new levels. Right? It is very hard to get partial credit. Although I have somehow had Williams students who've gotten half points on some problems. I'm not quite sure how half integral scores have happened. Go for the problems that you can solve. Put in all the details. Don't assume anything. Be very clear. Most of these problems have an elegant way of looking at them. You can sometimes solve them by brute force. And sometimes you can do the brute force in the amount of time you have to do the exam. It's much better to spend 3 hours working on just 1 or 2 problems and get those right than to spend your time working on a lot of problems and have nothing. I have had students who have applied to graduate school who have had bad GRE scores but good Putnam scores, and a good Putnam score trumps a bad GRE score, where schools have told me, oh, okay, no longer concerned. Because if you're coming from a liberal arts college, there's always concern, well, what did you really do in this class? How does that compare? Or if you come from Wasamatta U, a school that no one has heard of, how is that school comparable to a top R1 school? That's one of the reasons why people like GREs. The GRE, however, is a very flawed test. I will not say why while this is recording, but we can talk about that later. Putnam problems, if you can solve Putnam problems, that's a good thing. All right, so did anybody have a problem that just shouted out to them, I want to do this one? Or at least I have an idea how to do this one. I don't know if the idea will work, but at least I have a thought.
16A1.
16A1. So is that on the second? Which one is that? 2016A1?
Yeah.
Okay. So 2016A1 is the following. Let me just make sure this is in good. Okay. So 2016A1. Find the smallest positive integer j. So smallest j in n plus such that for all polynomials p of x with integer coefficients, I'm trying to abbreviate very fast, 2016 divides the jth derivative, and that's what the j parentheses means, evaluated at k. Okay, so we want to find the smallest positive integer j such that for every polynomial with integer coefficients, this is true. Every polynomial. So you can start writing down a couple of polynomials and try to get some intuition. And if you can find a polynomial that doesn't work for certain values of j, you then start getting some lower bounds for j. So do you have any thoughts on a lower bound for j? What were your thoughts for this problem?
Mine?
Yes.
I thought it had to do something like the lowest j such that j factorial, or 2016 divides j factorial.
Okay, so smallest j such that 2016 divides j factorial. So what might you want to look at of 2016? What might be useful to know about 2016? It's prime factorization. What should you have memorized before taking the 2018 Putnam? The factorization of 2018. You should also know whether or not 2018 is prime. If you do not memorize that, I will trust you to calculate that very quickly on the fly. That's the advantage of doing this in an even year. All right, 2018, let's do the factor tree. 2 goes, I'm sorry? Oh, 2016, thank you. So actually, when I look at that, I know the sum of the digits is 9, so I know 3 is going to go into that as well. So So I first pull out the 2, or I can even go better. I'll pull out the 6. And so 6 goes into 20, 3 times is 18, 2 over here is 3 is 18, then 3, so 336, which is also a multiple of 3. Oh, this was a multiple of 9. I could have pulled out a 9. That would have been better. Oh well. So I'll do a 2, a 3. I can only get a 3 from here, so then I'll get a 1, 1, 2. All right, well, 1, 1, 2 is clearly even, so I would get 55, 56.
7.
So I got 8 times 7, so I'll have a 2 cubed and a 7. So you get 2016 is 1, 2, I think 2 to the 5th times 3 times 7. Did I make a mistake?
3 squared.
Is 3 squared. It actually won't make a difference, I believe, that I dropped the 3 squared. But yes, we should have the correct factorization of 2016. So give me some values of j that you know there will be a polynomial that doesn't work.
Anything below 6?
Anything below 6. So when we try to, 2 to the 6, we would have to divide, the first 6 derivatives. And so we should be able to find a polynomial where this won't work. So I could probably try maybe p of x equals x to the 6th. And just when I start taking all the derivatives of this, I'm not going to have multiples of 2016. So this is going to force us to be at least x to the 7th. So now we know this implies j is greater than or equal to 7. Can we do a little bit better? So the question is, what's the smallest factorial that will divide this?
8, I think.
So if we do
has-
8 factorial, that's going to give us a 2 cubed from the 8, a 7. The 6 is going to give us a 2 times 3. Then we'll get a 5. 4 will be 2 squared. Then we'll get a 3, a 2, and a 1. So we'll have 2 to the 3, 4, 5, 6, 2 to the 6th. We'll have,
One more.
I'm sorry?
There's one more too.
2 to the 7.
2 to the 7th. All right, my algebra sucks, but it's good enough for what we need. Times 3 squared times 5 times 7. And if we did 7 factorial, we wouldn't have enough 2's. Yes?
Can we just go over again why we're looking at factorial? I didn't get that.
Well, when we take the derivative, we're going to get a j minus 1, we're going to get exponents coming down.
Okay.
So it seems logical for a problem like this that the factorization of 2016 is going to come into play because we'll get like a j minus 1, j minus 2.
What if there isn't enough in the exponent? What if it's just like 2 times x to the 0? Are you
Then
counting
you get
that?
0.
Right.
Then 0.
Well, one thing is we have to be careful because when we have things coming down, we're not going to get all the way down to 1, but we will get 8 consecutive numbers. So so here is 8 factorial, but what if I just did any 8 consecutive numbers? Will any 8 consecutive numbers have at least 5 powers of 2, at least 2 powers of 3, and at least 1 power of 7? So any 8, because when you start pulling down the derivatives, you'll get, say, k minus 1, k minus 2, all the way down to k minus 7. So for any 8 consecutive numbers, we will always get at least 1 7. For any 8 consecutive numbers, at least 2 of them have to be multiples of 3. So we'll always get the 3 squared. So what's the worst case for us if we have 8 consecutive numbers? Well, if we have 8 consecutive numbers, we have to have an 8, a number that's 0 mod 8. We have to have a number that's 0 mod 4, and we have to have a number that's 0 mod 2. We get exactly one of each. So in fact, while 8 factorial equals this, we know that if we ever have k minus 1, k minus 7 is a multiple of 2 to the 5th, 3 squared times 7. So no matter what polynomial we have, once we take at least 8 derivatives, all of the coefficients will be multiples of 2016. So this tells us that j is less than or equal to 8. We are now extremely close. The upper and the lower bounds differ by 1. So all we have to do is find one polynomial of degree 7 that doesn't work. Any candidates? Yeah. So x to the 7 shows we need j to equal 8. And so that resolves this problem. So the key insight is to start to think that a factorial is going to come. Yes?
Well, I guess.
Okay. So I'll pontificate first and then you will talk. Excellent. So the first thing is to notice that we're going to have products of consecutive numbers coming down. The simplest case to look at is if we take enough derivatives to go all the way down to 1. So we would get, k, k minus 1, k minus 2, all the way down to 1. That's got to be a multiple of 2016. Because we could have just the pure polynomial, x to the j, or x to the k. And in that case, then we start looking at, well, if we have 8 factorial, we'll have enough factors. The challenge is, of course, for other terms, we may not have numbers going all the way down to 1, but we realize, if we ever have consecutive factors, all that really matters is there's one factor in here that's a multiple of 7. There's at least 2 that are multiples of 3, and there's enough that are multiples of 2.
So thinking about the third level of stinginess that the Putnam graders operate on.
Yes.
I was just wondering, would this be how would you have just guarantee?
I would spend a little bit more time writing this up very carefully. I would say, here's the factorization of 2016, and I would get this. And then what I would say is, I would prove the following lemma. And I would write, lemma. For all n minus 1 dot n minus 7 is a multiple of 2016. And I would prove that. And then I would show if we have p of x and j is greater than or equal to 8, then each term is multiplied by n minus 1 dot n minus 7 times potentially more. And since this part over here is already a multiple of 2016, then each term is going to be multiple of 2016. And it doesn't matter what we get when we actually evaluate k. And then I would explicitly give an example of, so this would be 1, 2, this would be, I guess, 0, and then 3, I would look at x to the 7. And by looking at x to the 7, we see that there is a polynomial of degree 7 that doesn't work, so j has to be at least 8. And now we've shown that j equals 8 or higher always works. So now we know j equals 8. But if you want to try to write some of these problems up rigorously, I am happy to take a look at it, and I will give it to Kayla to grade harshly. She actually graded a green chicken exam problem a couple of years ago. There was a question on, what is the smallest number that has a certain property, and it involved rules for divisibility that she knew. And so she was able to just quickly tell you, does this answer match? If yes, she would give full credit, and then if it was not matching, she would then often flag it, unless it was really messily written, in which case she would just give no credit. So she holds the record as the youngest grader of a green chicken exam, and given that the green chicken exam is no more, she will probably hold that record in perpetuity. So this is a really good problem. And what it shows is that if you look at things the right way, it's not bad. The problem is, as you get deeper and deeper and deeper, to find the right way to look at these problems gets harder and harder and harder. But you have a huge advantage. The problem is solvable. There is a nice way. Otherwise, it wouldn't be a Putnam problem. This is different than life. Do you have one?
Yes, but also just really quickly for this one that we just did.
Yes.
So there's no bound anywhere that k has to be an integer, right?
If k doesn't have to be an integer, then you're screwed.
Okay. 'Cause I was,
Right.
Yeah, I was like.
So you are correct that it should explicitly state that k is an integer, because if k is not an integer, you could put in, for instance, pi,
Yeah, exactly.
and then, so to some extent, you can sometimes figure out what is meant
Okay.
by otherwise analyzing and saying, well, if they didn't mean this, then the problem becomes trivial or stupid or whatnot, and I would just put a little note
Okay.
and say, note, I am assuming you meant to say k is an integer, because otherwise I could just evaluate it pi, and then there will be no value of j that works. Because I could just look at the pure polynomial, x to the n. And then no matter what n you choose, if you take x equals pi, it's not going to be multiple of 2016.
Okay. Yeah. I was just confused by that.
Yep.
In terms of questions.
Yes.
Number 3 on the first page.
Okay, number 3 on the first page. Okay, so this looks
75.
fun.
I have the first one of this looks fun, not the second one, but I think I have.
All right, so this is 1989, number 3. We want p in base 10 is alternating zeros and ones.
Yeah. Starts with the one that says
So 1 0 1 0 0 1. How many? So before we analyze this, what are your thoughts? Finitely many or infinitely many? How many people feel finitely many? So why do you think it should be finitely many?
Does it ask you how many there are?
It could be infinitely many, right?
Yeah.
So, infinitely many is a possibility. But why might it be finitely many? So it's got to be entirely elementary, but you need to have if you have some idea of primes, the probability number is prime is 1 over log x. What this is basically telling us is every time we go up by an order of magnitude, we only have one candidate in our set. So really, let's call these numbers, an will be 1 0 1 0 0 1. And the number of digits we have is really going to be maybe 2n plus 1 or something like that. So this is going to be roughly 10 to the 2n plus 1. So your probability an equals prime is going to be about 1 over the log of an, which is about 1 over 2n. We got a log 10 as well, but yeah. And so if I wanted to calculate the expected number, well, that's actually giving me a harmonic series. So if I want to look at the expected number of such primes, it would be like the sum of the probability an is prime, and that would diverge. So maybe there are infinitely many. Again, it's extremely structured though. If I were to just randomly choose a number in each of these intervals and ask, do I expect to get lucky infinitely many times? This is telling me maybe yes. And again, what happens is when you get lucky, you get a contribution of 1. When you're unlucky, you get a contribution of 0. Every now and then things spike up. Yes?
You can show that if n is not prime, then it's not getting prime.
Okay, so if n is composite, composite. Okay, so did you have a factorization?
Yeah, kind of. Yeah, kind of.
Okay.
It's like you take, well, if n is divisible by, I don't know what you want to call them, n is divisible by.
So write n equals, say, AB.
Then if you take a sub a, it's not the best letters.
Oh, okay. So let's do km.
Correct. You take a sub k times,
So it's going to be 1 followed by a string of zeros followed by a 1.
yeah, so 10 to the 2m plus 1, yeah.
Something like that.
Yeah.
And you've got one extra 0 here, so this is basically going to be the length of AK. Is that what you were doing?
Yeah.
And then when you multiply, you'll get, when it hits this, you'll get the 1 0 1 0 1 0 1, and you'll get a 0, and then you'll get the 1 0 1 0 1 0 1 from that.
Wait, I think that's the case only if it's 2.
Okay, that's
You
the case
need-
only when
you
it's
need
2.
Then another long string of zeros and then another 1
Okay.
if it's 3. Do you see how I'm doing?
Right. Okay. So okay. So what's
It's not that clean.
okay? It's not that clear. Okay. So what's your one that works?
Um,
You're right. This is doing where it's 2 copies.
Yeah, plus, 1, 0, then the number of zeros equal to AK, then a 1,
And then the number of zeros equal to AK.
And you need m of those. And then you need m minus 1. You need m ones in there total.
And then this is like m times.
Yeah.
This is where you just have to be careful and put in the details. But I would first do, I was doing the case of m equals 2, building intuition from that, then take m equals 3, build intuition from that, and then see how you get it in general. And the idea is now when you put this in, it's going to avoid, and it's going to just fill in. So now we know n must be prime. Okay, so only candidates n equals a prime. Okay. Now what else can we argue? The number of ones can't be a multiple of 3. So how are we determining n? Is n the number of ones? What is our notation? Is that what you were using? N is the number of ones or the number of digits?
I would do the number of 1s.
All right, so n is the number of ones. So is this 2n or is it 2n minus 1? Or is it now like n halves, something like that? So if n is the number of ones, then in every pair we have 1, 1. So then the size of the number would be, twice the number of pairs.
I think it's just 2n.
But then we have that extra 1 at the end. So it actually might be 2n minus 1. Because the number of ones includes this one over here, but we don't have that 0. So I think it would be 2n minus 1 would actually be the size of the number. So if n equals 3, that would be the number 101.
Wait, if you
Oh,
do
no,
n
n
equals
equals
0
1,
once, then n equals 2 for 101.
Okay, great. So n equals 2 for 101. and we would get 3.
Correct.
Oh,
What, 10 cubed is not?
no, because
No,
the 10
the
cube.
number of digits. That's
Oh,
not-
I think it's just
Or-
2n.
Okay.
I think it's just straight up 2n.
Well, but if n equals 2, we want a number to have, roughly, to be of size roughly 100, which is 10 squared. And if n equals 3, we have 1, 0, 1, 0, 1. We want something of size 10 to the 5th. So it's looking like, if we doubled that, that would be 6. So we would have to subtract 1. If we doubled that, that would be 4. So the number of digits is, I think, 2n minus 1. So we have roughly 2n minus 1 digits. And so here, okay, so that gives us the number of digits. So we know that the only candidates is when the number of digits is when n is prime. So that means we have 2n minus 1 digits, and n is going to be the number of ones. So is it ever possible for n to be a multiple of 3? Other than just n equals 3. So that divisibility rule by 3 is not going to really come into play. I'm sorry?
Except for at 3.
Yeah, but that's one
Yeah.
possibility. So we do know that 101 is prime when n equals 1. No, that's not prime. What about n equals 3? Is that prime? So what goes into that? 3.
And something.
And so, right, because we see that we have 3 ones here, so we know this is not prime. When n equals 4, well, we already showed by that doesn't work. When n equals 5, you now have 1, 0, 1, 0, 1, 0, 1, 0, 1. So the question is that going to work? So the question is there some way to see that this can't happen? That once we get beyond 3, or beyond n equals 2, that there's going to be a problem? So I'm trying to think, can we write this as a nice sum? Like when n equals 5, it's going to be 10 to the, is it like 10 to the 8 plus 10 to the 6, or is it 10 to the 7?
No, I think it's 8.
Was it 9? Was it 9?
It should be
No.
It's 10 to the 9, right?
minus 1 digit instead of 2.
86420.
Okay, it's 86420. Okay. 8 plus 6 plus 4 plus 2 plus 0. And if we add that up, this is a geometric series, it's going to be 1 minus 10. So the ratio is 10 squared. So the next term is going to be 10 to the 10, I think, divided by 1 minus 10 squared. So this will be 10 to the 10 minus 1 over 99. Is that correct? Yep. So that is at least that is correct. So we would have a formula like this for all of our numbers. It's going to be something divided by 99. So the question is, can we find a common factor?
Oh, yes.
Okay.
Because never mind.
Okay. We know the top has to be divisible by 9 and it has to be divisible by 11. Just because we know this is an integer. But we need to know that the top is divisible by something else.
Well, because this number is 101, 01, 01, we know that those digits have to divide. So I'm pretty sure this doesn't.
Right, but 10 to the 10th minus 1. Isn't that just a bunch of nines?
Yeah, and then you pull them out.
Right. So this is going to be all 9s.
Yeah.
And when we divide by 99, we'll get 1, 0, 1, 0, 1, 0, 1. So the question is, what is the... Now, we could actually try to find the prime factorization. So factor integer 1, 0, 1, 0, 1, 0, 1, 0, 1. This is the advantage of half. So it's 41 times 271 times 9091. So if we had done that, which would take us a while, that's not going to be very illuminating. So the question is, are we now looking at this the wrong way? So I like the fact that we've eliminated any n that's not composite, but we need to find a way to generate other quantities. So do we start grouping things here? Every time we increase, we took a number and then we were adding another. The next time we would add a 10 to the 10, and then a 10 to the 12, and then a 10 to the 16. So one possibility is so here the factors are 10101010 is 41 times, we're cheating, 271 times 9091. What else might you want to look at? So this was the number with 5 ones. We could look at the number with 4 ones and see what we get for the factors there. Now we know that that doesn't work, but it might be worth seeing what factors we get.
We know they're all going to end in a 1.
So when we do 4, we get 73, 101, and 137. If we go to 6, we get 2 11s, another 101. So 101 as a factor is really good.
Well,
but that's 6, but we know about 6, right? So now let's go up to 7. When we go up to 7, we get 101011 and 111111. Oh, wait a minute. It somehow converted this to binary?
Yeah, I was like that.
Yeah, I was going to say, that doesn't look reasonable. All right, so it gets 239, 9090. So it's giving us 909091 as a factor when we have n equals 7. And again, this is cheating. So now, so this was n equals 7. Yeah, so it's automatically converting these to. Okay, so this when n equals 6, we get 9901. Although 6 might not be the best one to use. because we already know 6 is good. So if we do n equals 5, we get 9091. So let's try n equals 11. All right, so this is 5, 6, 7, 8, 9, 10, 11. Oh well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. All right. So I no longer get any nice factors involving the 9091s. Now I was hoping that maybe there's some kind of pattern with those as well. But that seems to break down. And looking at 13, nope, 13 is bad as well. So even if we take the time to do this, we're not getting anything that's helpful. And again, if we start having to really deeply factor the numbers, we're looking at it the wrong way. So in some sense, this is a great hint on all Putnam problems. If you have to spend a huge amount of time calculating things, almost surely you're looking at it the wrong way. So the question is, can we somehow go back to this expansion and find a number that must be dividing it? So the question is, is there any good way to see where these small prime factors are coming from, looking at small cases? Now, if you write a short computer program, absolutely illegal on the Putnam. But, since part of this class, this is not going to show up on the recording at all. So let me quickly. All right, so let's do for n equals 1 and less than equal to 20 n plus plus. X is equal to sum. And now if we have an n, what do we want to do? We want to sum 10 to the 2m, right? And m is going to go from 0 to n. Or is it an n plus 1? So if n equals, so if n equals 1, we go from 0 to 1, and then that would give us the number 101. Okay, so we might just be shifted by 1. Right. Then we can do prime q x. So if prime q equals true, print x. So I printed nothing.
I have a quick question.
Yes.
So the way you did your geometric series,
Right.
so if we did that for like other numbers, right? Like the denominator is always the same because 10 squared, right? And then the top, so here we had 10 to the 10th minus 1, right?
Right.
But like let's say we had a different number like 10 to the 6th minus 1, right?
Oh, okay. I see what the problem was. I've been so used to doing things in LaTeX, I used the wrong code. I put things in curly braces. I need to use, okay. So the only number that printed out as a prime was 101. So I'll go up to 200, it's still 101. I'll go up to 2000, it's thinking. It's still thinking. But I'm quite confident that the only ones it's going to find are 101. So there must be some way to find a good factor. There must be some congruence or something. So for the day after Thanksgiving, or when you're stuck at the Thanksgiving table, try to think about, can you find a factor? Yes?
But I just have a quick question.
Yes.
So like if we had like one of the numbers is going to be like 10 to the 6 minus 1 over 99, right?
Right.
So that tells us that 99 divides 10 to the 6 minus 1.
Correct.
So then, never mind.
Right. So we okay, it finished calculating up to 2,000 and it found nothing. Absolutely nothing other than 101. So we know. So one of the things I strongly urge you to do is have a black photo, so I can quickly, without having to walk all the way to the mute button.
Sorry.
Yes.
Okay, so you know that 10 to the 6 minus 1 divides 99 divides 10 to the 6 minus 1, right?
Right.
So then whenever you have a multiple of an even power, so like instead of 10 to the 10 minus 1, you had 10 to the 12 minus 1.
Right.
You can factor that into 10 to the 6 minus 1 and 10 to the 6 plus 1.
Okay.
Right? So then because 99 divides all of 10 to the 6 minus 1, you know you can pull out a 10 to the 6 plus 1.
Okay, so what you basically want to do, is you want to basically just say, this is a multiple, so every time I now have 5 of them, each one of them is going to be a multiple.
Right.
So that will give you things that are congruent to
So that
a
gives
certain,
you half of.
right, so that'll give you things that are congruent to 0 mod 5.
Yeah.
And we know, so you can keep trying to play games like that. And then we know if there's 4 things here, we know there's an issue. So maybe that's what you do, is that you keep having strings like this, and you know this doesn't work. So if we had, 10 to the 10, we know, well, okay, this is the one that works. But even though that this works, even though that this is prime, this 101 divides this, 101 divides, no, I guess 101 just divides this. So this one's not prime, this one's not prime. So the number that divides this is going to just be 10 to the 6th times that. Right? So something divides this because we know that's not prime. And then this number here is just 10 to the 6th times that. So now we know any number that has, 0 mod 3 factors is composite. And you can keep playing those games. If you just had 2 factors, well, we know 101 divides that. So anything that just has 2 factors, we know we're done. So I think that's the approach, is you just break it into groups of 2, groups of 3.
Then you just end up with the same. If it's composite, then it doesn't work, right?
Right, but
if it's still a prime number of them, then.
Okay, so the real issue here is that this would only work for composite numbers. So if we had.
But this is the n equals 5 case, right? So it would be, you have to do like a +1 rule or something, that you also have the 10 to the 0 too.
Right. So the difficulty would be is if we had a prime number of factors here, then you couldn't play this game of reducing it to something smaller. And so we might still be having to deal with that case.
Wait, but in that case,
If people have to go to the next class, go to the next class.
In that case, we've already shown that n composite doesn't work.
Right.
And this shows that n composite n prime shifted by 1 doesn't work, so doesn't that cover everything then?
So.
Because this is showing that the prime case doesn't work for n equals 5 at least.
No, well, the problem is we want to have a prime number of ones.
Right. Wouldn't you also have to prove that there's no consecutive primes for that to work? For what he's saying to work?
No, this doesn't work for n equals 5.
I know, but what he's saying that if you had n and then you have n plus 1, and you show that those two don't work, you still have to show them that there are no consecutive primes. What he's saying.
So.
But it doesn't.
Yeah, but you can't show that.
Right. All right. So we will leave this to be.
Well, aside from 2 and 3, yeah.